Hello and welcome to Mechanical Y. Today we will be discussing a brief history of our understanding of the atom, a fundamental building block of all matter. Now, as early as 500 BC, Greek philosopher Leucippus stated that all matter is made up of indivisible particles, and he called these particles atoms. Though for some time before Leucippus, and for many centuries afterward, many people of many different cultures tried to determine what matter was actually made up of. However, this was primarily done in a non-scientific, philosophical sense. Our current scientific understanding of the atom begins in the late 1700s. In 1789, French physicist Antoine Laurent de Lavoisier publishes the Law of Conservation of Mass, and shortly thereafterward he publishes a primitive periodic table. Several years later, in 1799, another French physicist, Joseph Louis Proust, comes up with his law of definite proportions. In the law of definite proportions, Proust states that different atoms of different elements come together to form compounds, and this laid the foundation for our understanding of how atoms come together to form molecules. However, our first major breakthrough of what the atom actually looked like did not come until 1803 with British physicist John Dalton. Now, in 1803, John Dalton published his model of the atom. Now, he stated that the atom was a solid sphere, and building on the work of Lavoisier, Dalton stated that atoms of a particular element are actually identical to each other, while atoms of different elements are different from each other. Dalton also expanded on the work of Proust with the law of multiple proportions, where after observing both carbon dioxide and carbon monoxide existing, Dalton stated that different elements can come together in different proportions to form different compounds. Now, after Dalton, things quieted down for about 90 years. No new major models of the atom had emerged in that time. However, experiments were still being performed. In particular, there was an experiment where two electrically charged plates were placed inside of a vacuum tube. It was observed that there was a beam coming out of one of these plates and going to the other, and this beam was called a cathode ray, after it was observed coming out of the negatively charged plate, or out of the cathode. In 1897, a British physicist John Joseph Thompson states that this beam is actually made up of particles, and thus we discover the electron. Now, Thompson set about trying to create a new model of the atom that would incorporate these electrons. He stated that electrons are actually found speckled across the atom in an even coat, and the atom is primarily a positive medium. Now, this led to the Thompson model of the atom, also known as the Plum Pudding model of the atom, because it reminded Thompson of the way plums are scattered around plum pudding. Now, this caused many physicists of the day to try to prove, disprove, or improve Thompson's model. Notably, Japanese physicist Hontaro Nagaoka disagreed with Thompson's model. In particular, Nagaoka stated that there must be a positively charged nucleus, and these atoms merely swirl around this nucleus. Nagaoka came up with what is called the Saturnian Model of the atom to reflect his theories. Now, in the Saturnian model of the atom, it is so named because it resembles the planet Saturn. Now, starting in 1908, different physicists tried to prove or disprove which one of these models was correct. New Zealand physicist Ernst Rutherford set out with a series of experiments. Now, these experiments were performed on Rutherford's behalf by Hans Geiger and Ernest Marsden, and these are known as the Geiger-Marsden experiments. Now, in the Geiger-Marsden experiments, they took thin sheets of foil, thin sheets of metal, and they bombarded them with particles. If Thomson's model of the atom was correct, these particles should pass through the atom virtually unhindered, and therefore the beam will be uninterrupted by the thin metal plate. However, Nagaoka's theories were correct, then there should be scattering as these particles collide with a dense nucleus. While Geiger and Marsden observed most of the beam to pass through the plates virtually unhindered, it was found that there was some scattering, and thus the nucleus of the atom was discovered experimentally. In 1911, Rutherford publishes his modified version of the Saturnian model, the Rutherford model of the atom, also known as the planetary model of the atom, because electrons resembled planets orbiting the nucleus which behaved like the sun. Originally, the nucleus was merely a concentration of positive charge. An element's location on the periodic table was based on the charge of the nucleus. However, in 1913, British physicist Frederick Soddy discovered that there were multiple elements in the same spot on the periodic table. Scottish physicist Margaret Todd suggested that these be called isotopes. Now, the official discovery of the proton in the nucleus was found in multiple steps spread out over several years. However, it is often credited to Rutherford as being for experiments he performed in 1917. Though isotopes suggested that there was another particle that was found inside the nucleus, though this was not discovered to be the neutron until many years later. Meanwhile, in other parts of Europe in the early 1900s, Albert Einstein and Max Planck are developing their theories on quantum mechanics and wave mechanics. And this gives physicists an opportunity to look at the atom in a new perspective. In 1913, Danish physicist Niels Bohr tries to apply Max Planck's and Albert Einstein's theories to the model of the atom. Collaborating to some extent with Rutherford, he states that electrons possess a particular place around the atom. In particular, Niels Bohr stated that these electrons are found in particular shells around the atom. And as the atom is excited, these electrons can jump between shells. And this led to the Bohr model of the atom, also sometimes referred to as the Bohr-Rutherford model of the atom. Next came some very rapid developments. In 1924, French physicist Louis de Broglie said that subatomic particles are observed to behave like waves. And this was supported in 1926 by Austrian Ervin Schrodinger, who stated that electrons were indeed a wave and not a particle. However, German Max Born stated electrons must behave both like particles and waves in order to reconcile some differences that he found in experimental data. And in 1927, German Werner Heisenberg comes up with his uncertainty principle, and he states that we cannot accurately predict the location of an electron around the nucleus of an atom. We can only predict a probable location where it might be found. And with this, we came to what is almost our current model of the atom. Now, in this model, we have a dense positively charged nucleus made up of protons. Now, around this nucleus, electrons swirl in a cloud, with their location being determined probabilistically. And we can't pin down exactly where these electrons are found. However, our final modern model of the atom did not come until 1932, when British physicist James Chadwick finally discovers the neutron. And with this, we come to our current model of the atom. In the nucleus, we have protons, and the number of protons determine the location of an atom on the periodic table. Along with the protons in the nucleus are neutrons, and the number of neutrons determine different isotopes of a particular atom. Now, around this nucleus swirl electrons in a cloud. Now, in this cloud, we cannot determine the exact location of an electron. We can only determine where that electron might be located. And here we have our current model of the atom. So is this the final model of the atom? Is this accurate? Well, if history has taught us anything, is that this is likely a flawed model, that there is much improvement still to be done. And sometime in the future, we're going to develop a new, more accurate model of the atom, where we will be able to better see what the atom looks like and how it behaves. However, to get to this point, it has taken many physicists over many centuries working diligently to try to determine what the atom actually looked like. And though each particular model was perhaps not as accurate as the next, it was an important building block to improve our understanding of what the atom actually looked like. Well, thank you for watching. I hope you found this interesting. If you did, please like and share this video, and please subscribe to stay up to date on new content.